Hello and welcome to this manufacturing process technology part 2 module 35. We were talking about e-beam machining in the last module, and we also tried to guesstimate the power for a certain material removal rate, and so there was a P equal to CQ relationship through which we got a ballpark value of the velocity at which scanning could happen of an e-beam system if you were to cut a slot on the surface of a metal substrate. So, let us look at a little bit of the mechanics which is involved or which is underlying of the e-beam process really. So, as I already have illustrated, the electrons are accelerated through a voltage and they have a very high overall velocity, about probably close to that of light, and these electrons are actually falling on the material, thus striking the lattice structure of the material, and there is almost always that a small layer of the material does not know. The electrons are so fast moving in nature. So, the layer that is there is a shell layer that is there which does not even feel that there is a beam, okay, which is hitting. So, if you look at some properties related to the masses of the electrons or the charge that they carry. So, you know that the mass of the electron is about 9.1 10 to the power minus 31 kg. The charge that they carry is about 1.6 10 to the power minus 19 coulomb. And so, the kinetic energy which would be obtained here is really half times of mass of the electron times of u square minus u0 square, and this is in electron volts where me is the electron mass. And obviously, if electron is accelerated through a potential difference V volts, the total amount of force that it experiences, the total energy that it ultimately has is the charge on the electron times of the voltage times of the distance through which it is moving. Okay. So, force distance product is the work done, and that is actually equal to the kinetic energy half me times of u square minus u0 square. So, if u were to be taken as the final velocity of the electron and u0 was the initial velocity and E is the electronic charge, and if we assumed that prior to the emitting or just immediately after the emitting, the electrons all had 0 electron velocities. Okay. So, or maybe very small electron velocities which are hardly comparable to the overall accelerated electron velocity that would result because of the perforated anode system. You already are aware of how the cup shaped tungsten filament creates the electron beams and focuses the electron beam into a perforated anode. Okay. So, the final expression that would come with plugging in all these values related to the electron mass, the electron charge, and the different let us say velocities which are taken into consideration, and let us say the velocity u is in kilometers per second further. So, this is given again with a relationship between the voltage that is there to accelerate the electron and the velocity in kilometers per second through a relationship equal to 600 v to the power of half. So, this takes care of all the coefficients like the electron mass or charge which comes by this expression, the total amount of work done equal to the kinetic energy. Okay. And so, when a fast moving electron impinges the material surface, it should really penetrate through a transparent layer, as I had illustrated earlier, till the lattice starts detecting the electron and starts converting the momentum of the electron into kinetic energy. Okay. So, when the collision process starts to happen, obviously there is going to be a temperature rise, and so this curly path here is really representing the collision process which has happened below a few layers which have been crossed as a transparent layer by the high velocity or high moving electron, and ultimately the electron is obviously brought to rest because all its energy has been transferred in terms of kinetic energy, and the temperature of this particular layer has increased to the level so that it can start vaporizing. So, the layer through which the electron penetrates again is called the beam transparent layer. So, this you must remember is a sort of a terminology. So, it is a beam transparent layer. So, it is basically as if the layer does not know that there is a beam. So, the heat generation that would take place inside the material obviously below the transparent skin would result in an increase in the temperature to the melting point. There would be or a vaporization point, and typically there is going to be beam splatter, mostly because if there is a skin layer which is there on the top and there is some kind of a superheat that is given to the metal vapor that has been created in a small cavity or a pocket beneath the skin layer would open up with an impact, okay, and so that can create or that can lead to some beam spattering. So, the total range to which the electron can penetrate, let us say delta, in this case would really depend on few things like kinetic energy, for example, of the electron. So, higher is the velocity of the electron, the thicker would be the penetration depth of the electron to the particular material surface, and this further would depend on the accelerating voltage, because the kinetic energy high means that the voltage through which the electron has been accelerated is also quite high. So, the total penetration depth in this case, which is also including the beam transparent layer. So, you can see here as the total range. Okay, so, it is a beam transparent layer, maybe delta dash plus delta double dash, the total layer in which collisions start to happen, where delta dash and delta double dash is equal to the total range of penetration or depth of penetration. So, that delta is empirically related again to both the accelerating voltage as well as the density of the material which is being machined, and in this case the empirical relation is 2.6 10 to the power of minus 17 square of V, okay, the accelerating voltage is a square divided by material density rho. So, delta is the range of, you can say, penetration and this is expressed in millimeters. V is the accelerating voltage, in volts, and obviously rho is the density of the material in kg per millimeter cube. Let us look at a numerical design of this estimation of the delta to get a ballpark idea of what is going to be the range of penetration depth and maybe while doing a normal e-beam machining on steel. Okay. So, we designed this problem from a real experiment that during drilling of holes in a steel workpiece by EBM, electron beam machining, an accelerating voltage of 150 kV is used. You have to determine the electron range of penetration. So, let us first look at what is the density of steel. So, the density of steel is about 76 10 to the power of minus 7 kg per millimeter cube, and penetration depth therefore can be given by the expression 2.6 10 to the power of minus 17 times of 150 kilovolts which is being used for the e-beam machining in this case. So, square of that, okay, divided by the density which is 76 10 to the power of minus 7, and this can be reported in terms of millimeters then. So, this becomes about 77 microns. So, you can already think of the extent up to which an e-beam can penetrate. It is about 100 microns, which is close to the diameter of a human hair. So, this much is the kind of penetration depth that would happen if the e-beam were to strike on a surface. Obviously, as the process is happening continuously as a function of time, the extent up to which the drilling would happen could be a through hole as more and more heat is added and more layers are disturbed within the surface. But for one such strike or one such penetration of the electron beam, a material an extent up to about 77 to 80 microns is the only kind of penetration depth which is covered in the process of doing this e-beam machining. So, let us now look at little different aspect about e-beam machining, and that is about trying to estimate what is going to be the temperature rise and trying to estimate what is going to be the depth of penetration through a heat conduction formulation. And again, just as I did in the EDM process, in this process also I would typically look at only the governing equations and maybe the boundary conditions, and then try to evaluate the solutions of those equations using the boundary conditions, so that I should get an estimate of what is going to be the maximum temperature or the maximum depth of melting temperature, or in this case vaporization temperature, which may happen. So, let us estimate that from first principles. Let us say the temperature rise can be approximated by solving the one dimensional, this is only a simplistic model, heat conduction equation for a heat source placed inside the metal. Okay. You know that in this case, it is not a surface driven heat flow, but actually the heat pocket that has been generated is within the material in this particular case. In EDM, of course, we looked at only a heat flow which starts from the surface inwards, and because of a spark coming and hitting the surface and disturbing layers from the surface layer onwards. In this case, the heat pocket is below the transparent layer, you have to remember that. Okay. So, placed inside the metal. So, if you look at a one dimensional heat conduction problem this way, so you have del theta as a function of z, which is the depth, okay, and time t by del t, theta is temperature here, okay, is equal to the thermal diffusivity alpha of the material times of del 2 zt by del t2, del z2 plus 1 by rho times of c times of the heat source intensity, which is also a function of depth z and the time t, h z t. Okay. So, here the various terms mean theta is the temperature in the depth direction from the heat pocket, okay. Alpha is the thermal diffusivity, alpha is the thermal dense diffusivity of the material metal, and z of course is the distance from the surface T is the time and HZT is the heat source intensity. You can say that it is the heat generated per unit time per unit volume. So, that is HZT. So, if we assume the heat source to be a steady heat source, the intensity would only depend on the depth from the surface and not time, right. So, you can actually have a relationship, a relation can be framed where Hz, the heat as a function of distance from the surface z is equal to A e to the power of minus Bz. Okay. A and B are sort of the energy absorption characteristics of the material. So, where I can say A and the small term B here depict the energy absorption characteristics of the material. So, if I just wanted to substitute this value back into the governing equation that I had earlier solved. So, substituting, or I had earlier outlaid. So, substituting the value of Hz in the one dimensional heat conduction equation, we get this d theta as a function of z and t by dt. Okay. So, the variation of temperature with respect to time would be alpha times the second differential of the temperature with respect to space Zt z square plus A by rho c to the power of minus Bz. So, this is what the value of Hz comes out to be. It is no longer time dependent because we assume that to be a steady heat source. So, the function of time, it does not change, only changes with z, okay, the depth from the melting temperature. So, now let us also further assume some boundaries. So, we assume the following conditions. One is that the metal body is semi infinite that we are looking at. So, the metal body is semi infinite. Okay. We can also assume that the surface of the metal is insulated except the hot spot. Except the hot spot, and we can further assume that the rate of heat input remains uniform with time, particularly during the duration of the e-beam pulse. Okay. So, the rate of heat input into the material, okay, remains uniform with time during the entire pulse duration. So, with these three conditions, if we were to solve the PD of the governing equation, we will get these trends of the variation of temperature with respect to Z. And as you can see here, that for different pulse durations, for example, T1 is probably lower in comparison to T2 in comparison to T3. T3 is the highest duration of the pulse. The values of maximum temperatures are also different. Okay, so for a lower duration beam or lower duration beam pulse, the temperature arrived at is quite obviously lower in comparison to for a higher duration beam pulse. And also the very fact that if the time duration of the beam pulse is more, you have the maximum temperature or the maximum hot spot which reaches within the material at a lower value of beam depth in comparison to that of lower value of pulse, because obviously it is a conduction process, and you can think of it that the material is conducting out in an outwardly manner from the vapor pocket which has been formulated, and there is going to be if supposing the duration of the beam is more, then probably the heat conduction time also is given to it is very high in comparison to a single small pulse of the beam. So you can think of it in this manner, that as the pulse duration increases, there is going to be homogenization of the temperature within the material, and the very fact that there is a boundary outside facing the atmosphere where most of the heat conduction would actually happen from the vapor pocket, it would seem for a higher pulse duration that the peak temperature sort of would shift towards the surface. Okay, so the various Z values which are reported from the surface or the vapor pocket which has been formulated for a higher duration pulse would be nearer to the surface, because it has enough relaxation time, I guess, between the pulse on pulse off durations for the heat to be properly distributed. Okay, so that the depth will not be much of an issue there, but if it is a sudden impact process of a shorter duration, then the beam transparent layer would obviously be thicker, and it would have very less time to relax and conduct the heat in an outwardly manner, as if you are localizing the heat in a vapor pocket which has been created at a few layers deep within the surface. So that is the reason why the temperature would kind of the maximum temperature or the peak temperature would kind of be nearer to the surface for a higher duration beam or higher pulse duration than a lower pulse duration. So these are some of the learnings that we have from the solution for temperature as a function of Z and T. Remember, in this case it is quite different from the case of a spark machining process where it was a surface inward driven phenomena. Here it is a vapor pocket outward driven phenomena. So the two are completely different in terms of the basic physics and the mechanism that goes in for doing the machining operation. So I had earlier talked a little bit about how the scanning velocity can be affected as a function of power, and we had generated a very first estimate or a guesstimate of the power versus MRR. Let us now look at a little alternate way of arriving at this through semi experimental means, and we will perform some dimensional analysis based on the parameters which we think are important for this whole beam material interaction process, and through the dimensional analysis we will probably arrive at some governing equation where we could actually correlate all these parameters together, where there could be the velocity of scan, there could be the melting temperature of the material, there could be the thermal conductivity of substrate, there could be the beam voltage, so on and so forth, so that we have a nice estimate of a more appropriate estimate of the scan speeds of the beam. So let us actually look at such process. This is E-beam, I am sorry, EBM. So we will use we will now use dimensional analysis for estimating the functional characteristics of the beam process, and we will probably apply the Buckingham's pi theorem here. But before doing this, we probably try and have a look at what are going to be the most important parameters for a process of beam matter interaction in the beam machining case. So, the quantities of interest are obviously beam power. Okay. So, you could have the power as accelerating voltage beam current product. So, accelerating voltage into beam current, that is what beam power is going to be. You have a beam diameter d, you have velocity of the beam with respect to the workpiece, I will call this V. We will also have another important property which is very much related, which is thermal conductivity of the workpiece itself, of the workpiece. This is the value K. Obviously, the volume specific heat of the metal. So, volume specific heat of metal, which is rho c in this case, the melting temperature, we call this theta melting, okay, and depth of penetration of the melting temperature, which is going to be Z. So, you have to understand here that we are talking about, you know, from the vapor pocket, what is going to be the depth onwards, which would lead to the formulation of the melting zone. So, the temperature estimation would be done in a manner so that T equal to T melting, you know. So, to include a zone behind aside or beside the or around the vapor pocket, which would create a melt pool, you know, because of the zone conducting heat in an outwardly manner from the vapor pocket, which has been formulated within a few layers of depth of the material. So, these are in general all the parameters which are associated with the beam matter interaction in this particular process. And what we are going to do probably in the next module is to sort of create some groups, some non-dimensional groups, which are going to be important for the Buckingham pi analysis. So that we are arriving, or we are able to arrive at dimensionally consistent relationships between these various parameters. And then later on we can also have some empirical you know, experimental empirical relationship to correlate to the relationship formulated by dimensional analysis, so that we can get an appropriate expression for the beam power versus beam depth. So, with this I would like to end up this particular module, and in the next module we will probably do further analysis on this beam power to depth. Thank you and goodbye.